Testing.
Some of that.
1, 2, 3.
Dr. Ray Ward founded Ward Laboratories in 1983. Ray received his bachelor's and master's degree in soil science. Ray received a BS and an MS soil science degrees from University of Nebraska in 1959 and 1961, and a plant science PhD from South Dakota State University in 1970.
Good enough.
I'll let you go.
Okay, thank you. And where's Ray? He's not. He's working. Yeah, it was kind of funny when he was talking about how old he was yesterday. And I got 25 years on him, or 24 years on him. And the things I've learned in the last 10 years are probably the most exciting since I got my BS degree. And for you guys in here, I kind of like to tease NRCS a little bit. But I got my BS degree in soil conservation. And I went down to the state office and made sure I had a job with Soil Conservation Service in 1959. And when they said, okay, I'm going to Washington County, Nebraska, which is just north of Omaha and Blair. You need to take this physical, and they give me the papers, and I went down to February, Nebraska, to the other doctor, not our doctor, and because he was a federal examiner or whatever. And he pulled this book out about that thick and started flipping charts and wanted me to identify things on those pages. And then I took my physical back to the guy that hired me, and he asked me what the color was on the wall, what the color was in the paintings, and said, we can't hire you. And that's when I finally figured out that color blindness was really a serious problem. But it was the best damn thing the government ever did for me. So this is kind of the title today, and then yesterday you guys said you want to learn about Haney. So that's what I'm going to start with, is the Haney soil test, or the Haney program. Just to give you an introduction, and as we go through some of this stuff, I'll put a few things in comparing Haney and what we're doing right now. Rick says that my harsh chemicals are just too tough on the soil, and we need to do something a little different. And so he has the Sulfita 24-hour CO2 burst test. You've seen those advertised in magazines, and maybe you've seen them. And that tells you the microbial activity. It's really biological activity. And have you noticed that the dry years we've been having? And last year in the soil tests, we had tremendous carryover nitrate. And the guys had good corn yields, irrigated, but we had nitrate tests high enough in 8 inches of soil to make 0 nitrogen recommendation for 240 bushel corn. And as for irrigated, the soil would, between irrigations, would get dried out in that topsoil. And then it wet up, and then it dried down, and then it wet up. And the CO2 burst test, you take a dry soil, wet it, and it gives the amount of CO2 released in 24 hours. And that's bacteria. And so they would gear up, and the bacteria then are really high nitrogen consumers. Their carbon-nitrogen ratio is about 3 to 1. And then when they die off, that nitrogen is released. And then it'd come another dry spell, and then wet irrigation, and then more nitrate, another cycle, and it just built that nitrate up. And begin to realize how important this microbial test is to release nitrogen. I'm not sure how it all works together yet, but we're learning that. And then another thing he does is water-soluble organic carbon. So we do a water extract on this dry soil. And we get the water-soluble organic carbon, and then percent MAC is percent microbial active carbon. And Rick says that the water-soluble carbon is the carbon or the food for the microbes. Not the total organic matter, not the total carbon in the soil, but the water-soluble stuff. That's what the bacteria get a hold of, or the microbes. And so he's looking at that carbon. And then water-soluble nitrogen, which is a nitrate, ammonium, and organic nitrogen. And then we subtract the nitrate and ammonia from the total nitrogen to get organic nitrogen. And then we calculate organic nitrogen ratio. And that ratio should be between 8 and 15. We're working with a guy up at Eureka, South Dakota that just inherited some land. He said the land is overgrazed. His carbon nitrogen ratio in the native range is 20. or 22. And so the grass is struggling because it's not releasing nitrogen. We need to get some legume type plants in there to make the nitrogen more available. And so we're trying to talk him into interseeding some legumes into his native grass. And then that organic ratio there. And then we got water soluble nitrogen, I told you that. So these are things on the report now that you see. Total nitrogen, inorganic nitrogen, organic nitrogen, and then we have H3A, ICAP, and Rick calls that total P. And ICAP, I'll show you pretty soon what that thing is. And then we have H3A, FIA, flow injection analysis, and he calls that inorganic P. And then H3A, the difference between those two is organic P. And so these go into his calculations. And then he has a soil health test, that's the one that we're kind of the goal you're looking for when you get all these analyses. That's a Solvita test divided by the carbon-nitrogen ratio. This is organic, water-soluble organic carbon-nitrogen ratio. Plus organic carbon divided by 100 and plus organic nitrogen divided by 10. And so that's the soil health test. And the goal is to keep increasing that value. So if you're starting at 4, you want to increase that. Now he says at 7 is one, if you're above 7, then you feel you got pretty good activity and health in that soil. So those are things on our farm where I did some of this. We had 5 on 2 fields, and then where I had corn is third-year corn, which is interesting, but I have night crawlers growing in this field, and the test on it was just above 7. So there's some differences there that we're trying to look at.
Does that matter if you have a growing crop out there versus, say, fallow?
Yeah. Haney, Rick said that he really sees his test as being used after harvest in making plans for the next year. Now we're also doing, in addition to this part of the soil health, we're doing phospholipid fatty acids, or PLFA. There we want to take the samples when we've got active growing plants. And in that case, we'd like to have our soil samples taken 0 to 6 or 0 to 8, whichever depth you're at, like we do for regular soil samples. Sample near the root system, or near the plant, I mean. And near 10 to 15 cores mixed together for a composite sample. Okay. On the PLFA, we don't necessarily need to put it on ice. If it's hotter than heck outside, I guess you'd want to, but put it in a cooler so the temperature stays the same. And you could have some ice in there if you wanted to, but just to keep the same temperature. And take
So say like you have growing wheat, would you want to do that like in the spring time?
I would want to get some full tiller. It's when I would do that in the spring. Now, if you've had real dry, and I did this in August on the soybeans and corn, and I had a real high bacteria count, not much fungi, and I think we got a rain, and then I went out maybe a week after the rain. I don't think everything's back up to. So it'd be nice to be able to take it at a time when maybe moisture's been kind of normal for at least 10 days or 2 weeks. I think it would make a little difference. Or otherwise, I got such a bad system. And I was on corn, bean, wheat rotation with cover crop and wheat, and I thought it was pretty good. His test has shown me some things.
Yeah.
I'm going to talk about how the soil health test correlates or ties into the traditional soil test.
Yeah, a little bit.
Okay.
And you guys ask questions. I forgot to say that when we started. You guys ask questions on these things, and I'll get as far as I can when they shut me off. And then maybe we can cover the rest of it in that after 10 o'clock. And I intend to stay here until noon, but I want to be in the car at 12:01, heading back to the car. So that's what we'll do. And this is our laboratory, and we have 15,700 square feet. We're making plans right now. I haven't got anything back from the contractor yet. Then I have to go talk to the banker and make sure I can do this. But we're going to add on 16,900 square feet, or 130 by 130 foot building. And then we're going to do our sample receiving and processing, and then preparing the extracts in that new building and be behind this lab, and keep our instruments here where they are, and just kind of eliminate some of the dust and stuff. So here in front is, this is our phosphorus station. It's called flow injection analysis. Here are the inductively coupled argon plasma, the ICAPs that we talked about. Then we have behind there is another flow injection for nitrate and sulfate. Way in the back of pH and organic matter and some of those things. Over here on this side is where our soil health is, and we have some equipment in there now that we're using, and it's not organized very well because we're waiting to get some better space for it and set this up. And so we're doing the phospholipid fatty acids and the Haney tests and those kind of things. And the problem with the Haney test that now we can run, like on the ICAP, it runs a sample every 20 seconds. On the Latchet, it runs a sample every 40 seconds. On the organic carbon test, it one sample every 15 minutes. And so we're going to be limited on how many of the soil health tests we can do. So we're going to have to kind of pick some zones to sample, and because we get a lot of grid samples on our irrigated fields in Nebraska, and we're running right now about 3,700 soil samples a day. And maybe we should always start with pH. Rick says he can tell pH from some of his tests, but I decided I'm going to add pH and organic matter to the Haney test because I want to see that. And that's because I've been seeing it for 50-some years, but this is there's 2 electrodes there, so it reads 2 samples at a time. And then if the pH is below 6.5, we add a buffer solution. After an hour, it comes back and finds those and reads those, and then the girl takes those 3 trays out and puts the next 3 in. So we got 4 of those instruments doing that. Oh, by the way, those are made in Australia, so trying to get things run is kind of bad. It's fixed sometimes. Do you need to know any of this stuff? I don't think so. I assume most of your soils would be calcareous out here. Maybe over on the east there would be some acid soils. I think I see some down in the 5 sometimes. What causes the soil to get acid besides weathering?
Organic matter.
No, organic matter. Organic matter would.
Increase the organic acids.
Well, but they're not very acid, if I can say it that way. And it's nitrogen and sulfur fertilizer. Nitrogen. 1 pound of nitrogen neutralizes 1.8 pounds of lime, and 1 pound of sulfur neutralizes 3.6 pounds of lime. So some of these dry land corners in fields, the guys have pHs down in the 5s, and their irrigated field is 7 or 7.2 because they're getting lime out of the irrigation water, the calcium magnesium out of the irrigation water, and that keeps the pH up on the irrigated, but it's in corners. It'd be more in the sandy soils than in the healthy soil. Just flow injection analysis, and just show a picture up close. Each one, there's test tubes there. There's 90 test tubes in that rack, and each one of those test tubes is a different soil sample. In the case of phosphorus, we're using malic 3 as our main extract, and so those are malic extracts in there. And so it's 360 samples on that auto sampler. We got 4 channels, so we got 4 auto samplers that are running. We can run that. Set that up, and so we're running 360 times 4 samples at one time. It takes about 3 hours to go through that. And then we get set up and get the next batch running. Won't bore you too much more on that. And I put this in here because on the flow injection analysis, we run nitrate, sulfate, phosphorus, and chloride with this kind of instrument. And we do run Bray, because there's some customers who want Bray P1. Bray P2 once in a while, and then Olson P we run. So we'll run any of those.
What's the difference between those 3, the malic?
The malic 3 and the Bray, when the test is below 50, and the pH is not calcareous, or soil is not calcareous, they read almost the same. They're very similar, so I call them the same. The Olson is about, if you divide it by 1.6, or if you took Olson times 1.6, you'd have the malic comparison test. Now the Bray doesn't work in calcareous soils, and that's where Olson come in with his bicarb test, because Bray developed a test that's hydrochloric acid and ammonium fluoride, And when you get about 4% lime in the soil, the lime neutralizes all that acid, and then you have a water extract. Well, Malik, when he developed the Malik 2, and I met him in 75, and the first thing I thought, he's finally agreeing to Bray because he had half the acid and half the ammonium fluoride of the Bray test. Then he added ammonium chloride so he could extract cations, and added acetic acid as a buffering acid so he could keep the pH down and extract phosphorus out of calcareous soils. Well, the lab in North Carolina got ICAPs in, and there were the emitters, this emitter that the nozzle that the vapor goes up through into that flame would plug up all the time from the chloride. So Malik made 3, and it's nitric acid and ammonium nitrate instead of the hydrochloride or chloride ions. So the Malik 3 is the same as the Malik or the Bray on the concentrations, buffered with the acetic acid. So it'll work on calcareous soils. What we try to do is when we get west of the divide, we run Olsen P on everything to the west of there. And to the east out here on the plains, we run the Malik 3. But if you have some desire for the other, you can do that. So we go with the nitrate test first, and my goal is, the idea is to end the growing season with less than 5 part per million nitrate in the root zone. The 3-foot root zone, 5 part per million is 50 pounds of nitrogen, or nitrate. If you can live with 50 pounds, but on samples we get from Burlington, sometimes there'll be maybe 200 or 250 pounds of residual nitrate, 2 feet. So we got a lot of residual nitrate. Now, probably doesn't leach very far. In Nebraska, it does, because we got more water and we're pumping too damn much. And that was one of the disappointing things about the guy yesterday afternoon. He never said, we got to cut back on water. And maybe out here that's okay, but in Nebraska, our guys are still pumping too much water because they're doing too much tillage and all those things. But so it says potential movement below the root zone if it's higher than 5 part per million. And when we moved to Kearney in '83, we had irrigation water that had 55 part per million nitrate in it, 110 pounds of nitrogen for 9 inches of water. And that was because they were over-irrigating, mainly. And then because they're over-irrigating, they're leaching nitrate, and then they would put 200 pounds of nitrogen on.
I don't want to drink much of that water.
Make your hair shine. One guy at one time had 35 part per million in his water, and he was 70 years old. And he said he's going to keep drinking because it hadn't hurt him yet. But it's if you got really stomach problems, digestion problems, or young babies, then it's a very serious problem. But otherwise, I think we treat it pretty fast. So if you have the nitrate, you see nitrate's water soluble. It's easy to extract the nitrate out of soil, and we're using a calcium phosphate solution that we use for sulfur also. And because it's soluble, we can do that, and then we can quantify it. We can calculate the pounds of nitrate that's in 8 inches, or in 2 feet, or in 3 feet. However we want to do that. By taking 0.3 times the soil depth in inches, and that equals pounds per acre. So that says every inch of soil weighs 300,000 pounds. And the tolerable rate on soil erosion, the T is 5 tons. 5 tons is 10,000 pounds. You take 30 times 10,000, you have 300,000 pounds. In 30 years, 5 ton loss, you'll lose an inch of topsoil. And you guys say that's okay.
Well, somebody says that's okay.
I know somebody does.
That's not our guy.
Thank you for correcting me.
And we can lose more than that in less than 30 years.
Well, yeah, that's
We can lose that
our
one.
nice thing. So, well, we go on. I'll get off track all the time. With these
Quit
topics.
digging us.
So here's the way we calculate nitrogen for crops, and corn, if you've seen me talk before, it's 1.2. I dropped it to 1.1 this fall because Haney says he's using 1, and he's subtracting nitrate, ammonia, and mineralizable nitrogen, I'm subtracting just nitrate. So I dropped it, because it's got to think about this. In corn, you take the grain off. You take it off 0.65 to 0.7 pounds of nitrogen. We're using 1.2. You got 5,500s, the 50 hundredths and 5,500 pounds of nitrogen left. Been doing this for 30 years. Where's all that nitrogen going? Now, you can argue some of it's going in organic matter. We are increasing over time our organic matter some. And each percent organic matter, rough number, is 1,000 pounds of nitrogen. So Scott, when you said you increased your organic matter 0.2%, then you've increased 200 pounds of nitrogen in that soil. And that organic matter means fertility, so to speak, as a residual fertility. So I decided to cut it down to 1. How soon will I cut it to 1.0? I'm going to see how the farmers get along with this and see. And then the wheat, I still 2.4. We're using pretty close. I'd like to use 2.4 on our farm. And we have a farm down where I grew up in southeast Nebraska. And I put on, I guess, about 100 pounds of nitrogen, and I got 58 bushel wheat. But then I planted cover crop, thinking that there'd be some residual nitrate. Most places the cover crop looks pretty bad. So that means that the wheat uses it, if it puts it in the straw or whatever. And then milo, I got 1.1 grass, 35 pounds per ton. Millet, I'm not sure about that. 1.7 sounds right. It sounds a little bit high to me. Scott, would you use it?
I'd say it's probably a little bit high.
Okay. Where would you?
We're shooting for like a 30 bushel yield. A lot of times we're like at 20 pounds to 30 pounds of nitrogen.
But you don't
is
know how
what
much,
we actually put on.
Yeah, how much nitrate's in the soil? Have any idea?
I would, yeah, I wouldn't want to guess right now without having it in front of me.
That's pretty smart. So then we'll just do the nitrogen pounds per acre yield times nitrogen requirement minus nitrate in 24 inches. And if you don't send in a subsoil, I just assume, you know what assume means too, but I assume you got 25 pounds in the subsoil to make that correction. And then any legume credit and then manure credit, you're going to subtract that nitrogen out of that thing. And then in Nebraska, irrigation water credit is important. This is just an example of 200 bushel corn. I don't know why I put that one in there. But 100 pounds, 30 pounds of nitrate in the soil, 190 past soybean crop, 40, 150. And then if we have irrigation, then we got 20 pounds there, we'd be down 130 pounds of nitrogen for 200 bushel corn. And the interesting thing is guys might make plans and have a recommendation for like 220 or 230 bushel corn, or growing close to 300 bushel, haven't changed a thing. And so I know that the system will supply more nitrogen than what we're saying is needed. If they'll keep their yield goals kind of modest instead of going way over. That was interesting because the farmers make their yield goals based on what just happened. So the last fall, the yield goals are all down 20 to 30 bushel. You know, they're back up.
Now with $4 corn, they gotta raise a lot more.
Yeah. Are they going to do like they did in the 30s and the wheat price went down, so they're going to grow more wheat? And you know, that logic just doesn't make any sense. And where we got water shortages, wouldn't it be nice to put a cover crop in and have cattle graze it, or put wheat in the rotation? The Haney nitrogen is ammonia, nitrate, mineralizable nitrogen, and that calculation is based on the Savita test and a water-soluble organic carbon, water-soluble organic nitrogen ratio. So those are the three Haney nitrogen things that we get out of that test. And these two here are the H3A test. We run nitrate and ammonia on the water and on the H3A. And if there's a big difference, we know we have a problem. If they're very close together, which they should be, and usually are, then we know we're on the right track. Part of that is just a safety thing that's in there. The H3A test that Haney has is Haney, Posner, and Arnold is what that stands for. But the extract is 3 acids that roots exude or a leak out of their system. And Rick, that's what he did his PhD on, worked on those kind of things, and he said there's about 90 different chemicals that leak out of the root system to feed microbes, to make the microbial activity around that system. And he thought the three that were consistent for all plants was malic, oxalic, and citric acid. And they're very dilute solutions, but and that's what the plant's leaking out, so the microbes can, get that food, get that water-soluble food, and then supply the nutrients to the plant. How that all works, hear Ray talk about those things, but I'm still skeptical.
Just a quick question, because of the business you're in, but you also have a farm,
Right.
could you use enriched strips on your farm to evaluate how well the test is capturing the information?
I think we can, I don't have enough time to talk to my tenant and make sure he gets all these things that I'd like to do. And so I I turned the farm is in Farmers National Management, and the manager is an agronomist. He got a degree in agronomy, so it's very good. And I started it when I bought the land from my sister in '92, and so I hired him because then I wanted I could tell him what I wanted done, and he could go talk to my nephew that never did ask me a question. That's how we got started on all this stuff. And then he decided to quit farming, and so I got another tenant. And he's a young farmer, and he's got a kid that wants to come back to farm. And I really like to get him to attend some of these meetings and see some of this. But he's doing some things because of what he sees in our farm. Phosphorus, this is an old slide I use. We have phosphorus that sits on the outside of soil particles, and we've got phosphorus inside, which is fixed. I used to use the term fixed some, and there's a lot of people that talk about fixed, and you hear on the radio that only 15 to 20% of the phosphorus available, the rest of it's fixed, and all that baloney crap, and don't believe any of it. The phosphorus is there, sets on these particles, and then it diffuses off of there out in the soil solution as the plant takes up phosphorus, then more comes off, and so that's a constant thing changing. And as long as you have big enough supply here, then you don't need to put any more on. And if you put it on, it goes onto these surfaces. And there's lots of surfaces, and the roots can't get to every one of them. And why it's only 15, 20% available is because the roots can't get all the soil particles, but the phosphorus is there, and next year you'll have it. So you keep, my idea is to keep this kind of thing in a level where you'd like to have it. And we have these ratings, here's the Olson and the Malic 3, and hopefully, by the time you're up here dry land, up to medium, up to 25 or 15 here, maybe put on 20 pounds of phosphorus. If you're above 25, you don't need to put any on. And when you drop below 25, you put a little on, and as it goes above that, and then Ray and some other guys, what Dwayne Beck talks about. Dwayne Beck's got an Olson P of less than 5, and he doesn't put any phosphorus on, and he gets tremendous corn yields. But I run total phosphorus on the soil for him, and he has 800 part per million. And most of our soils are around 400 part per million, so he's got big reservoir of kind of total phosphorus that the mycorrhiza can dissolve and keep supplying that plant. But as a farmer, landlord, I'm not sure I want to be able to extract and all that. Because, I guess I got some slides in to show that. But what happens when you take that phosphorus off that land every year after year after year? And Gabe Brown even asked me, where can I get phosphorus from fertilizer? There's no free phosphorus. There's free nitrogen all over the place that we can get, but not phosphorus. And eventually you're going to have to put it on. Do you want to extract it now and let your generation, next generation, or third generation down the road put it on? Or would you like to maintain it now? That's my stewardship type comments that I make on that thing. On the irrigated, we cut it off at 50 on the irrigated. I tell the guys, well, if you're going 300 bushel of corn, maybe in the 40 part per million range. I've been saying 35, but the corn yields keep going up. So some of that. So those are the kind of things I look at on the recommendation. If you're down low, you're going to take quite a bit. In this low range here, 50 bushel wheat, take out about 30 pounds of phosphorus, I think. so we'll show that here. How's a Malic 3 compared to the Haney test, an ICAP? And this is just a little bit of data I have. Here's our phosphorus test, and here's the Haney test. Now that dilute solution of that organic acid is dissolving more, or extracting more phosphorus than the Malic 3. And Rick calls my test a harsh chemical test. So it's interesting to me that those weak acids are sucking that much phosphorus out of that soil. But they correlate. You know, here's the low one, that's the lowest one over here. Here's the highest one in both cases. So I think there's a relationship between those. And the way I look at that is that I can use the Haney test to refine my Malic test for recommendations similar. So if you guys want to argue with any of these things, you can. So. Sulfur, and I don't know about you, but I think that's one of our most limiting factors of dryland in Nebraska. Because we know how to put phosphorus or nitrogen phosphorus. Sulfur is one that we really need to think more about. When in southeast Nebraska, we've had, and I've been putting some sulfur on, but the county agent, the university person, is very conservative. 2 years in a row, he's had the brightest wheat fields, brightest yellow wheat fields, and hopefully he's learned his lesson now. But here's wheat takes about 3/10 of a pound of sulfur per bushel. 50 bushel wheat, 15 pounds of sulfur. And if you got some in the soil, that is a 50 bushel wheat here, you got this much sulfur required by this request here, and I say about 6 pounds of sulfur would be, it doesn't take very much. And you put a little bit on. If you want to lower your pH with you have a calcareous soil, just put a little bit of sulfur on. You're never going to change the pH, so don't worry about it. 4% lime in a foot of soil, it takes 16 tons of elemental sulfur. So don't try it. Just put a little sulfur on, supply it around. And the sulfur and the Haney, here's our sulfur test here. And this thing, is pretty comparable again. So, and Haney, these are things we're doing in our lab. So when we run the test, Rick's making NPK recommendations, but I'm following sulfur, calcium, magnesium, zinc, iron, manganese, copper too. So I got all this information to go along with this. And it's pretty interesting kind of things that's going on. So again, it tells me I think we're doing pretty good. Here's the lowest test here. There's it doesn't match as well as the phosphorus, but it's pretty good. And chloride is one that I don't know. You guys have any chloride needs out? Do you know if guys are putting that on wheat? Are you doing anything?
We've tried it a little bit, and we've had neighbors that have tried it a little bit. Sometimes you see tremendous results, sometimes you don't see anything from it.
Yeah, and I think once if you put on kind of the recommended amount, you'd probably have enough for 3 to 5 years.
Yeah, we were doing some custom cutting for a guy, and we went around the field with the combines, and we got to the south side, and you could actually see where the sprayer ran out the V pattern. And we didn't know what he did, so we asked him, and he told us that the wheat looked really bad that spring, and the agronomist come out and said you need chloride on it.
So if you're above 6 part per million in 2 feet of soil, and we just assume if you got 6 in the top, you got 6 in the subsoil if you don't have a subsoil. And then you don't need it if you're above that. If you're below that, then put some on. And South Dakota State and Kansas State have recommendations for chloride. Nebraska can't get response. So South Dakota is 60 and Kansas State's 30 as a zero, if you zero test. So I'd use 45 and just make the recommendations that way. And if you got chloride in irrigation water, it shows up. If you put chloride on, it'll show up in the test. So I think it works. It's one of those that maybe you need to be thinking about it. And it only take 5 pounds of chloride. Now this is ICAP. In here is that inductively coupled argon plasma. You ever heard of a plasma welder? It's the same thing. That argon makes it, I don't understand the physics at all, but it makes a real high temperature. And the temperature in there is between 6 and 10,000 C. So when this solution from here goes in here and this vapor goes up in there, every element gives off light. And there's different wavelengths of light depending on the concentration of the element. And so the computer picks out the wavelengths for the concentrations we're after. And then it makes a calculation based on our standard curves, and that's how we calculate that stuff. But it's pretty interesting, and these instruments are tabletop. Before these come out, they're all floor models. And they had the light would travel from that flame a meter to photoelectric cell tubes here, was the old ones. And then that light would shine there and it'd pick up this wavelength, and then that was for whatever element. Those wavelengths are all different, so you set your tubes where you capture them. Well, now this machine has a flame, a mirror, and it bounces back, and that light is hits a square about an inch square, and it can pick up 250,000 wavelengths. It's just amazing what's going on. These are made in England, and the auto samplers are made in Omaha, just to see how things are put together. $125,000 for that, right there. So I got 5 of those. Another year we'll have to get another one or 2. Potassium. I don't know if you should have good potassium in almost everything except really that coarse sand that you showed that picture of. I don't know if there's anything in there.
We do have, every once in a while, the soil tests show up that require potassium, but we've never done anything with it. Maybe we need to, but we never have.
I think you got more problems than potassium.
Potassium hasn't been our limiting factor, we don't feel like.
And we have some soils, sandy soils up in the northeast, north central part of Nebraska on the edge of the sand hills. That'll be down as 40, 35 part per million. Interesting, you put potassium on, you don't change the soil test. I think either the potassium has been fixed again or it's been leached. And then this is, I'm sorry about the time, but you heard about nitrate leaching? You know, nitrate moving down this. Do you know that nitrate can't leach by itself? It has to have a companion. For the chemistry people, they know that nitrate's an anion, and to keep that balance, you have to have a cation, negative, positive, and negative charge. And normally that's calcium that leaches down with that nitrate, but it could be potassium. And those are the kind of things that fascinate me. We have all these guys over in Iowa and Illinois checking nitrate in the tile drains. And they should be checking everything because they're losing everything. They're losing calcium. And now when I was in Tampa last week, they're finding phosphorus in that drainage water. So we got high enough phosphorus soil test that it's moving down and coming out the tile drains, which is unheard of if you ever went to college. And we told you phosphorus didn't move, which is pretty much a stupid fact. It does move over time. So here, this is the Haney K, and this is our ammonium acetate K. And this one's quite a bit different, but they are related. Here's a high test, and here's a low test. And so I think they can be used and show about the same things. But it has a lithium citrate as a buffer solution, and lithium would be a exchanging ion for the cations. And so it's a pretty weak solution, so I think that's why we're not pulling out too much potassium. But it's interesting that they do correlate. Zinc recommendations, and Scott, you were saying this about the recommendation for zinc, and that, see, in your dry land, well, that's probably, you could probably say 12 years. So if you put on, 1/10 or 2/10 of a pound of zinc a year, 12 years, you might be up to where you could be. So I don't feel bad at what you're doing. But make sure it's soluble zinc. And that's either dry as 36% zinc or a liquid. But there's some zincs out there like 20% that you put that on, you're just wasting your money and your time because you need soluble zinc to raise that. And this has been the way that University of Nebraska and Colorado State set that zinc recommendations up, in the early 60s. So I always stayed with that. And in Nebraska, we have zinc deficiency as a most critical trace element. And guys that are bringing, taking wheat ground and starting to grow corn and milo, they need zinc on a lot of those. But the irrigated ground is pretty good. And this is our DTPA test and the Haney test, the comparisons. And it just intrigues me that that acid that Haney says these plants are exuding and how they're extracting these nutrients like the other soil tests are doing. And which tells me that Haney's test isn't bad. Okay, just a few things then on the nutrients that bothers me is here's 60 bushel wheat, 30 pounds of phosphorus is taken out with that grain, 72 pounds of nitrogen, 16 pounds of potassium, and sulfur 7, and chloride's 4.2, and then zinc is 0.2. So when you take that grain off there, in Nebraska, or down where our farm is, that land was broke in the 1870s. We never put any fertilizer on until about 1960. So that's 90 years we grew crops without any fertilizer, other than the manure that we fed that's the nutrients to the cows, and then we took that out of the barn and put that on the land, and we grew sweet clover and alfalfa for nitrogen. But we extracted the nutrients. And I just read something from Gail Fuller. If you get Gail stuff, and there's a comment in there from Gabe Brown, I think it was, that this Anderson from somewhere said that our food today has 40% less minerals in it than. Now, how in the hell do they know that? And I'm going to go get an old feeds and feeding book and look at the standards in there compared to what when we do feed testing today, and see what the difference is. But think about this: you broke the native prairie, and you have all this organic matter, and you know the curves that the first 10 years we got rid of 20% of our organic matter, kind of the normal thing. And then in Nebraska with a 5% organic matter, it drops 20% in 10 years. We dropped 1% organic matter. We went from 5 to 4. Dropping the organic matter 1% released 1,000 pounds of nitrogen. So the pioneers had really good fertility with organic matter decomposing. And when that released phosphorus and potassium, all the plant nutrients that are in organic matter. And we can't build organic matter without having all those nutrients in there. And so we had really good fertility when we broke the prairie. Now, the other way it would be is that today we got a lot of starch in our grains. Maybe in the olden days they had the big germ and not as much starch, so naturally it'd be higher in minerals because the germ's got more minerals in it than the starch does, of course. So those are the kind of questions. I'd really like to see somebody take a variety of whatever crop from the 30s, they're stored out here in the mountains, and compare that to what we got today, side by side in the same land, and see. I think the nutrient level will be the same. And it's because our fertility's changed, because of farming and beating the hell out of the soil. And can we bring the nutrients back up by building organic matter? These are the questions that we got to answer. And the corn, 0.7 or 100, this is 200 bushel corn, but 0.7 ton of nitrogen, 0.33 on phosphorus, 0.23 per bushel on potassium, sulfur, chloride, and zinc. So if you go back, here's these nutrients, here are these nutrients. Anything you take off the land, you're taking nutrients off. Now, how are you going to replace those nutrients? That's the question, and that's why I was hoping Ray would be here, but because he says those guys are growing those crops without fertilizer. Now, if they had too high a fertilizer or too high a soil test, fine, use that up. But if they're low, sometime that's got to be replaced. Now, Scott's bringing in nutrients as compost and putting them back on the land. If we take corn to China, we need to bring those nutrients back that's in that corn. And how are you going to do that? But But when the guys say we're running out of phosphorus or whatever, that's because we're not recycling the nutrients. We haven't lost any nutrients other than what's went to the ocean, but we got to think about how are you going to bring those nutrients back. And if you're and then the Chesapeake Bay and the lake area and all those places got real high animal concentration. Why in the hell don't we feed the animals here and ship the animals there so we can put the nutrients back on our land instead of shipping the grain there and then they're polluting stuff? You know, this is how dumb we do things. Just.
They need to put us.
You're
in
recording
charge.
that too, aren't
That's what
you?
You know, they need to put us in charge for the day and
Yeah,
we'll get that fixed.
I think, yeah. But you know how the arguments that are coming up.
Well, part of the thing as far as not using fertilizers too is they're not growing a commodity crop every year. Now, does that make a difference?
No,
They're not trying to make a commodity crop on every acre every year.
right.
That's the way they're not. That's the way they're eliminating the commercial fertilizer.
Okay, if say you're going to go a cover crop and graze it, and the cover crop's going to fix nitrogen, fine, and maybe the mycorrhiza will dissolve some rock phosphate in the soil, some mineral phosphorus. That's fine. But eventually, you're going to, when you put the commodity crop back on there, or the food crop back on there that you're going to haul off, you're going to haul those nutrients off. And you delay it a year when you have a cover crop, and the animals are going to return the minerals right there.
Right.
And so when you're grazing, you don't have a problem.
And just to follow up on that question though, but if a farmer like Gabe or somebody has a regime where over a long period of time, 10, 15, 20 years, the soil organic matter is going from 1.5 to 4.5, does that not make sense that that is a sustainable system or a regenerative system?
Yeah, and I, you know, to me, I've been to Gabe's farm. And I know Gabe has Kelton and Galvay herd, 350 cows. He has a feedlot. And I know manure's been put on some of these fields where he's talking about.
Mm-hmm.
So he's returning nutrients to that land, and so he has real high nutrient level, I think. And so he doesn't need to put any more nutrients on there. But I'd like to know if he has a field that's far away from the farmstead, what's he doing there? And then how soon would the crash come is the next question. Because Elaine Ingram, she said in a meeting up in Minot that you put this compost tea on and you encourage the microbes and it goes down to the bedrock and dissolves minerals and brings them up. And I thought, how in the heck does that happen? And number two is we don't have bedrock. Now, in Nebraska, it's all less down there. And there's just too many of those if type things. And I want, I don't want you to overuse fertilizer. And I want you to be able to make your soil less healthy. But if you're going to build organic matter, you're going to have phosphorus come from somewhere to go into organic matter. You have to have nitrogen go into organic matter. You have to have calcium go into organic matter. You have to have zinc go into organic matter. And if you take that element out of the organic matter, you destroy the organic matter. And so, if he's building the organic matter that much, he's had to add a lot of nutrients to that.
From somewhere.
From somewhere. Yeah. Well, these are tough things, and we're kind of off the subject. But I was hoping you guys would talk about that. This is how we run organic matter. When it's lost on ignition, we have soil we put in here, and then we dry it at 105 for 2 hours to get rid of the moisture. And then we put it then we weigh it. Then we put it in an asher at 360 C for 2 hours. And that burns off the organic matter, and then we cool it and weigh it again. And that loss on ignition, we call it LOI, is our organic matter test. It's a very nice, clean test, and it works very well. And this has two balances back here. The grippers are there, picks up 2 at a time, and then we got another one that picks 4 at a time that reads those things. And when we have these robots, the thing that I'm thinking about is I need to get a robotic engineer so we can build our own dang equipment instead of paying somebody else from Australia. But we got to have the software to run these things, and we can buy the parts, I think, and make these things. So, and this is a picture from our farm, but to kind of change the water, And here I left this little bare strip here, had a few marrow growing here, but this Sudan grass growing here. And we went here in May the next year and took a cell sample from here and over here for moisture. And we had a ½ inch more moisture over here than we had on this bare wheat stuff. Because the sun was shining down here on the ground in April and early May, and over here this was laying down flat, covered the ground, and we were saving water. And that's the part that we got to get people to understand, I think, in some ways. And this is the deal Mark Watson's put together, a spiral with crop residue. Crop yield gets crop residues, saves soil water, makes better crop yield. You need more crop residue, saves more water, and kind of goes around that cycle. And if we can start building organic matter the cover on the soil, we can start increasing yields. It's all based on keeping this crop residue. So when you graze it off, or you haul it off, or the wind blows it off, you've lost the moisture. And then the other thing is, in the web soil survey, you guys know you can go in there and find the water holding capacity. This happens to be a couple soils from Sydney that did a talk out there a few years ago. And here's a Duroc loam. It holds 6 inches of water in 60 inches. And here's an Alliance loam that holds 9.8. So when you're managing the system, if you can only hold 3 or 4 inches of water in this soil, what kind of crops are you going to plant? Those things that don't need much water, that mature pretty fast. And if you got like 10 inches of water or 12 inches of water in 6 foot or 5 foot, then corn fits into that system. And those are the kind of things you got to think about.
Have you heard Dietrich Castens talk about that? That was one of the things that drove them away from summer fallow. He runs all them numbers. He's a spreadsheet guy.
His detail just drives me nuts.
But he figured he couldn't figure out where like 4 inches of his annual precipitation went because he was filling his profile, but his profile would only hold like 75% of his annual precipitation, and that's when it dawned on him he was losing it somewhere.
Yeah, that's why I put these together from what you listened to. Water and soil, and there's available water. Of course, the sand, I think you guys know sand won't hold as much water as the silt loam. You should know that. And then the granular soil structure, and this is from our farm down western, the thatch on there. When you get rain, it's nice, I kind of hate to show some of these soils. And I showed this to my wife one time. She said, "What the hell's that red thing?" I said, "Well, that's my spade." You got to have a spade. And then this is out of Mark Watson's at Alliance. This is a summer fallow field next to his no-till. Have you guys seen this kind of thing? I pulled that right there. I pulled that out. It's about 3/4 of an inch thick. I just pulled it out of there. Roots are growing on top of it, underneath it. And then the tillage, look here. This is prismatic structure down here. And so what the tillage does is breaks your structure up. Now you think about that. When you break the structure up, and if you're working land and you got an inch of rain, and you left your tractor in the field and you wanted to go get your tractor, would you drive across like you just worked? Or would you find a grass strip to drive home? and it got rain there too, but it's soil structure. Tillage ruins soil structure. And so then it compacts and all that stuff. When you stop doing tillage and you start building those aggregates, those water-stable aggregates, and doing all those things, then you start getting the strength of that. And this is the culprit for you SCS guys, or NRCS guys. It's a raindrop, and we got to protect the soil from that first to get that energy. So, a guy called out to the field, walked into the field, and you see this white. You can see the field being white, and there's that crust, about 1.5 inches deep there. Corn couldn't get up through it. Guys claiming chemical injury, and it just dug that, and then you wonder about that white. Well, you think about it, raindrop pounding on that soil, and you got sand, silt, and clay particles. Which ones are the biggest? Sand. And so the clays are down here sealing this up. And then you got the silts, and the sands are sitting up on top because they're the biggest. And then when the wind starts blowing, 8-mile-an-hour wind, will start those sand granules spinning. Saltation, you get wind erosion started. So you get a big rain on a black summer fall. Next afternoon it's blowing. Or maybe the same afternoon. It's blowing because you've got the sand up there to do that. Just that simple. Ben Anderson is a young farmer at Curtis, Nebraska. He had a soil He was taking my soils class I was teaching at UNK, and he couldn't do the lab, so he come out and we did some things. Here's 8 years of no-till farming. This is first year no-till farming. And we stirred those with a glass rod like that. We went across there and then took a picture. And here are these water-stable aggregates still in there together. And so I had to do a water holding capacity study. Then we took a 100 mil graduated cylinder, put 100 grams of soil in it, and then we could measure how far the soil was here so you get a bulk density. So then if the wet so many mils of soil, you can tell what the water holding capacity was. Kind of a simple test to do. But this first year no-till, and the water went down here. See the water sitting up here, sitting. And I come back the next day and this air gap is in here. And after 3 days of sitting there with this cover on top, I decided I better take a picture of that. Because you can see that there's a waterfront right down here. This is dry soil here, and that's kind of where the water went. Now, you remember the circle with the soil with the 4 parts, the mineral part, the air part, the water part, and the organic matter. When the porosity is at 50%, 25% water, 25% air. So when the water goes down in here, what happens to the air? Push ups. And there's enough heavy water up here pushing down, and this is lubricated enough because of the clays in there. And the air broke that seal right there, pushed that up. That's what happens when you have crusted soil. When you get a rainfall and it gets crusted, it seals it. Now air can't get out. If you can't get air out, what can't get in? Water. Oh man, I wonder. I'll go back here just a little bit. So I was out we live on the Wind River in Kearney, and we had in 2008 we had a couple of floods, and my wood pile was floating away. I was kind of mad about it. I was walking down there trying to figure out where it was going, and my wife saw me and hollered at me because it's about that far from going over my irrigation boots, and she'd get out of there. But the water's making a funny sound. So I went back the next day and they're making that same funny sound. I looked down, and water's about that deep, and there's little bubbles coming out of that water. It made me realize as water was going in that soil, the air was coming out. And so you think about this, you water this soil, you irrigate it, go get a rain, water goes in, pushes air out. Then as the plants use the water, air comes in, you get rain, and so all the soil is a great big lung, bringing oxygen in and pushing carbon dioxide out. And the way you do that is with good soil structure. Good water-stable aggregates and granular structure, and then the prismatic structure and the V rising, and those kind of things. And tillage breaks that structure and breaks that breathing process and the water penetration process. So I had this evaporation, and the thing I decided that farmers don't understand, they think if you don't have anything on that land that's black, that you're not losing any water. It just bugs me. And so I found this a little bit here in evaporation factors. Soil is different than open water surface because opportunity for evaporation is not always 100%. Can be more or less. Evaporation decreases as the soil surface dries out. Therefore, more rain is evaporated in frequent, small frequent storms than in large, infrequent storms. But a large infrequent storm, if you're a black fellow, runs off anyways. So it's, but the small rains evaporate when you got that hot surface there. And so the capillary rise affected by soil texture is less in sandy soils and more in clay soils, which I think is obvious. The presence of vegetation, shading effect. You know, you want to shade that ground as soon as you can with a new crop, and you want residue on that ground to keep it from the sun beating on it anyway. And then these other two really aren't much. And so then I got these slides from Gary and Gary Peterson. Inefficient water storage. Less than 25% of the precipitation is stored in the developer. That's from Gary's research. And he had stations at, I think, Sterling, Burlington, and Walsh, or somewhere in that kind of way. High erosion potential, grassy weed problems, large loss of carbon. research objectives: maximize precipitation use, improve soil productivity, increase economic return. And so they did these research on the summit, side slope, and toe slopes. And I don't know all these details, but some of the things they collected: yield, soil, water, soil, organic carbon, physical properties, and some of that. So, and then he's got kind of a summary in here. Here is the cropping systems: wheat fallow, wheat corn fallow, wheat corn millet fallow, and then opportunity and continuous. Did he have any continuous cropping in those experiments? Does anybody know? You know, and that's a sad part. Why in the hell do you have to have that fallow there? What is the matter with the western Kansas, eastern Colorado farmer? They think you have to fallow.
You guys will tell you all the time they got a fallow to raise wheat.
So why do you want to raise wheat?
That's my exact question. Who said, where does it say that we have to raise wheat? And the next answer to that is, well, that's what we've always done. To which I reply, if that's what we've always done, let's get the buffalo out here, because they did that a lot longer than we've raised wheat.
So it just, those are the kind of things. So what have we learned? Grain yield in 2 years, 3 years, 4 years. Cropping system, 4 years, and this is 1 year fallow in here. But in that 4-year system, they grew more grain per year than they did in a wheat fallow system. And then he says, why? How can we produce? And this, do you ever ask this question to him? How can we produce more with the same amount of water? And what principles can be derived from the data? And so he has this stage 1 in orange, July after harvest, and high temperature, dry soil, and a wilting point. So you really don't have much moisture going on here. And in September, well, 10 to 35% of precipitation stored. Stage 2 is in the winter, low temperatures, surface goes to field capacity, 50 to 85% of the precipitation is stored.
But we don't get very much during that stage.
Yeah, but you save all of it.
We would hope.
What was that? You want it to be higher?
He said, you hope.
Oh,
We would
yeah.
hope, we would hope.
And then the red stage, high temperatures, wet soil profile, field capacity, and you store 5